Hi, this is Dr. Bricker here with some hints for homework number 5, which is over Chapter 9, so we're skipping around a little bit. Chapter 9, Impulse and Momentum. Let's take a look at the first problem. Okay, so the first problem is 9.3. A student throws a 120-gram snowball. Okay, so the first one, the mass, 120 grams, so 0.12 kilograms divided by 1,000 at 7.5 meters per second, so that's the initial speed. 7.5 meters per second at the side of a schoolhouse where it hits and sticks. So we could assume that when it sticks, its final speed is equal to 0. And we want to know in part A, which I think there's only one part actually, what is the magnitude of the average force? So the average force on the wall if the duration of the collision is 0.16 seconds. Okay, let's sketch this out. Okay, so I have a mass of 0.12 kilograms, initial speed 7.5, final speed of 0. They're saying how much is the average force on the wall if the time of the collision is 0.16 seconds. So there's a couple of varieties of problems in this chapter. The first one deals with the impulse relationship. So J is impulse, and really it's just another name for change in momentum. So P is momentum, which is final momentum minus initial momentum. And momentum is mass times velocity, so mv final minus mv initial. Several ways of writing it. Whoops, not squared, vector sign. Okay, or m delta v is another way of writing it. So several ways of writing impulse, change in momentum, final momentum minus initial momentum, mv final minus mv initial. Oops. Yep, equals to m times delta v. The little vector sign here just means you have to consider the x direction separate from the y direction. Okay, so that's just emphasizing that. Okay, so this is a problem where we have mass, initial velocity, final velocity, time, and we're looking for force. So we've got another technique to solve some problems. It's this impulse relationship. Now, if you want to, you could actually figure out what the acceleration is, because you do know the initial speed, final speed, the amount of time. You could figure out the acceleration. Then you have the mass, and you could figure out the net force. So you could do it with stuff that we've done before. It just takes a little bit longer. Really, we would be using this kinematics equation. mv final is equal to mv initial plus at. I could multiply the whole thing through by m. mv final, mv initial plus ma times t. And then really, mv final, that's the final momentum. mv initial is the initial momentum, whoops, plus ma is the force times the time. So final momentum minus initial momentum, moving this to the left-hand side. Scoot this up a little so you can actually see it. Put the initial momentum to the left-hand side. This would be f times time. And this really is the impulse relationship. We've been using it the whole semester when we were talking about kinematics. It's just the m divided out. So if you put the m back in, then you come back with the impulse relationship. So you could do it the same way that we've done it before with kinematics and Newton's second law, or now we have this. So it's meant to make our lives easier. Okay, so let's actually solve this problem then. So it's a hint. Mass, velocity, force, time. Think impulse relationship. So I'm going to write it up here to save some room. Force times time, mv final minus mv initial. And the final velocity is actually 0. So this is the force that's going to be on the whatever was thrown. I think it was a snowball actually. So we're trying to figure out this force. So again, this term is 0 minus mv initial divided by the amount of time. And then we have everything. There's a minus sign here. Again, that just indicates that the direction of the force on the snowball is opposite direction that was actually moving. So you can put everything in here. Minus 0.12 kilograms. Initial speed 7.5 meters per second divided by the time, which is 0.16 seconds. Good. And then we have a kilogram meter per second squared, which is a Newton. So whatever that turns out to be, newtons. The answer you want to actually enter is the force on the school, I think it hit a school from the snowball. So it's you don't enter the minus sign for what they're actually asking. This is the force on the snowball from the school. We want the force on the school from the snowball. So whatever you get here, enter the positive value. Okay, great. Okay, 9.7, we have a graph. We know the mass. It's given to us. So the mass is 1.9 kilograms. Object's moving to the right in the positive x direction with a speed of 1.2. Okay, good, 1.2 meters per second. And we want to know a few things here. The object experiences the force as shown in the picture over here. Okay, so again, whenever you see a graph, what's actually being graphed? Force in newtons, time over here. Okay, good, so excellent. What is the object's speed after the force ends? Okay, so the speed after the force ends, so like the final speed, you know, the later speed. What is the direction of the object's velocity after the force ends? Okay, so for part B, if the final speed turns out to be positive, you're still moving to the right. If the final speed turns out to be negative, you're moving to the left. And let's see. Object experiences a force as shown in figure 2. So let's look at figure 2. Okay, so now this force is negative. This force just means it's in the opposite direction. This force would tend to slow you down. Okay, so part C is really a lot like part D, or sorry, part C is a lot like part A. It's just that the sign has changed. Same thing about part D. If the speed comes out to be positive or negative, that tells you which direction it's moving. We already know it in part B, it's got to be to the right. The force is positive. You're moving to the right. So the force is just going to make you speed up here. So this has got to be to the right. In part D, we don't know yet. This force is going to make you slow. Whoops. This force is going to make you slow down, but does it actually make you change directions? We don't know that yet. You'll have to actually work that out. Okay, so whenever you have a force versus time graph, the area under the curve here will be the change in momentum. So force times time, this value gives you the change in momentum. So we could figure out the area here. It's 2 newtons times a half of a second. So that would be 1 newton second. That's what the impulse is. That's what the change in momentum is from the graph. Okay, let's sketch this out a little. Okay, so again, the mass was 1.9. The initial speed was 1.2 meters per second. We want to know how fast we're going after this 1/2 second. And we can see the area under the curve here. Force times time just gives you 1 newton. So the area under the curve, force times time, is the change in momentum. So mv final minus mv initial. So F times delta t plus mv initial is going to be equal to mv final. So I've just added mv initial to both sides, and I'm trying to find the final speed. So that's what I'm working with here. Again, I'm given things like mass, velocity, force, and time, so I think impulse relationship immediately, and then I go about working to find out what I don't know or what's being asked for of. So F delta t plus mv initial divided by m, so this whole thing divided by m will give me the final speed. And it's going to come out to be positive, which it should. And that's part B. Part C is the same problem. It's just now, in part C, the force is negative. So the force is making you slow down. So do the same thing in part C. It's just that this F delta t term is going to be minus 1 newton. And then you'll have to see if this comes out to be positive or negative. Okay, excellent. Okay, so the next one, a Little League baseball game. The 145 gram ball, so immediately change that into kilograms, 0.145 kilograms, divide by 1,000 to do that. Enters the strike zone with an initial speed of 17 meters per second. The batter hits the ball and it leaves the bat in the opposite direction with a speed of 22. Okay, so if we're saying 17 is the positive direction, if it reverses direction, they don't tell us this is minus 22, but it's got to be negative 22 because it's headed the other way. So if I say 17 is positive, 22's got to be negative. And then what is the magnitude of the impulse delivered in part A? And part B, if the contact time was 1.1 milliseconds, so in other words, 1.1 times 10 to the minus third seconds, what is the average force? Okay, good. And it's just the magnitude of the average force. And that's all you want to know. Okay, so let's take a look at this. Okay, so the average impulse, the magnitude of the average impulse. The impulse is just the change in momentum. So mv final minus mv initial. And we just want the magnitude of this. So this will be 0.145 kilograms times negative 22 meters per second. And then minus, I'm going to run out of room, so let me write it over here. Minus 0.145 kilograms times 17 meters per second. This will come out to be negative. We just want the magnitude of it. So what you want to enter is just the magnitude. So just the number. So if you notice here, impulse units here, kilogram meters per second. That's the same thing as a Newton times a meter. We've saw that in previous problems. So let me just show you. A kilogram meter per second. If I multiply the top and bottom of this by seconds over seconds, I end up with a kilogram meter per second squared. That would be this part, times a second, which is a Newton second. So in other words, a Newton second is the same thing as a kilogram meter per second. So impulse, sometimes you see it like this, sometimes you see it like that. Okay, so the magnitude of the impulse, this is what you need, but just, the positive of that. And then part B is similar to what we've already done. Now that you know the impulse and you know the time, you can get the average force. Remember the impulse, which now you have from part A, is force times time. So if you're looking for the force, which we are, the average force, impulse divided by time will give you the average force. And again, we're just looking for, we're just looking for the magnitude of this. Okay, excellent. Okay, so 9.13, a small 150 gram cart is moving at 1.4 meters per second on a frictionless track when it collides with a larger 1 kilogram cart at rest. After the collision, the small cart recoils at 0.85 meters per second. So it goes the other direction, keep that in mind. What is the speed of the large cart after the collision? So this is the other sort of problem that you might see in this chapter. If there's an outside force, which we've dealt with in the previous 3 problems, then you have the impulse relationship. If the outside force is equal to 0, we have conservation of momentum. Let me show you what I'm talking about. Okay, so first of all, here's the information I have. I've labeled this as mass 1 moving at 1.4 meters per second, recoils in the other direction, minus 0.85. They don't give me the minus sign, but they say it goes opposite direction, so I'm putting minus there. Mass 2 is 1 kilogram. Initially it's at rest, so 0 meters per second. Oops, and then we want to know how fast this one's moving after the collision. So the picture something like this. Here's mass 1 going this way with V1 initial. Mass 2 is here, initially at rest, and then after the collision, mass 1 heads back the other way with the V1 final. Mass 2 is going to go this way. How fast is it going afterwards? Okay, so here's the impulse relationship. Now if the outside force is equal to 0, so the left-hand side is equal to 0, the initial momentum is equal to the final momentum. So whenever you see a collision problem, this is the way to deal with it. The total initial momentum of the system is equal to the final momentum of the system. So momentum of mass 1 initial plus momentum of 2 initial is equal to momentum of 1 final plus momentum of 2 final. Okay, I'm just adding things up. This is what I had to begin with. This is what I had later. They have to be equal to each other. The nice thing about this problem is mass 2 initially is not moving, so it doesn't have any momentum. And then I could fill in the details. M1 V1 initial, and then plus 0, so I'm not adding that. This would be equal to mass 1 V1 final plus mass 2 V2 final. And I know both of these, I know both of these, I know what mass 2 is. So a little bit more algebra and you can get V2 final. Let me just do one more step. Okay, so put this up to the other side, divide by mass 2, that will give you V2 final. And be careful with the signs. Initial. This one recoils, so V1 final is negative 0.85. You have to make sure that you put that in here. Okay, good. So that's a collision problem. Whenever you see collision, think again, the initial momentum of the system is equal to the final momentum of the system. Okay, next one, a man standing on a very slick ice fires a rifle horizontally. The mass of the man with the rifle is 70 kilograms. Okay, so the combined mass is 70 kilograms of the man and the rifle. Okay, the mass of the bullet is only 10 grams. So divide that by 1,000 and you would get 0.010 kilograms. Right, divide it by 1,000, move the decimal place over 3 spots. If the bullet leaves the muzzle with a speed of 500 meters per second, what is the final speed of the man? So when the man is standing on ice and he shoots the rifle, the bullet goes one way, the man and the rifle have to recoil the other direction. And we want to know what is the final speed of the man and the rifle together. Okay, let's solve this. Okay, so I have man and rifle as big M, massive bullet, we'll just MB, speed of bullet 500, speed of man and rifle together, they call it V final. Okay, so the man and the rifle are going to go this way with speed V final. The bullet is going to go this way, and it's just I just called it V bullet, and this is the mass of the bullet. So this isn't really a collision per se, but there are internal forces involved. And believe it or not, there's no momentum created. Before the explosion where the bullet goes one direction and the man goes the other way, there's no momentum, no net momentum. So afterwards, there's no net momentum. Whatever momentum the bullet has to the right is balanced by the momentum of the man on the rifle to the left. Whoops. So momentum of man plus rifle going one way has to be equal to momentum of the bullet going the other way. So the momentum of the man and the rifle would be, I call it big M V final. That's a certain amount of momentum this way. That's got to be equal to the momentum of the bullet, which is the mass of the bullet times the velocity of the bullet. And then you can figure out the speed of the bullet afterwards. So the man and the rifle are a lot more massive than the bullet, so you'll see that this will come out to be a lot smaller speed this way. But a bullet traveling at 500 one way could have the same momentum of something a lot more massive going the other way. Okay, great. Okay, next one, we have a 10,000 kilogram railroad car, so a lot of mass there, 10,000 kilograms, rolling at 6 meters per second. Okay, good, 6 meters per second. When an 8,000 kilogram load of gravel is dropped in, and then what is the speed of the gravel? What is the car speed after the gravel is dropped in? And it's sort of like a collision. This railroad car is just rolling along. Suddenly, this mass appears. It's just dropped in. It doesn't have any horizontal momentum. So whatever momentum the railroad car that was empty has is now being shared between the railroad car and the gravel. So let's sketch this out. It's a collision problem. Okay, so I've got the mass of the car. I just called it mass 1, 10,000. Mass 2, 8,000. This one's traveling at 6 meters per second initially. What's the combined speed afterwards? So the initial momentum of the system is equal to the final momentum of the system. Now the initial momentum of the system is just contained in the empty car. So mass 1, velocity 1, initial. And I didn't write the momentum of the substance that was dropped into the car because it's not moving horizontally. And then afterwards, now we have a combined mass. Mass 1 plus mass 2 times their combined speed. So this is a completely inelastic collision. They stick together. So when you're reading through the chapter, you've come across that term. It just means sticks together. So mass 1, velocity 1 initial, divided by their combined mass will give you their combined speed. Okay, so you can see it. This car's got to slow down if the mass suddenly increases by 8,000 kilograms. So completely inelastic collision. Okay, the next one, we got a 300-gram bird flying at 6.4, sees a 10-gram insect heading straight towards it at 29, as measured by an observer on the ground. The bird opens its mouth wide and enjoys a nice lunch. And then what is the bird's speed immediately after swallowing? Good, so it's sort of another collision one. It's a stick-together collision. The bird and the bug are now one, so they've got a combined mass. Let's set this problem up. Okay, so I've called the bird mass 1, the bug mass 2. The bird's moving at 6.4 meters per second initially. The bug is moving at 29, but towards the bird. So if the bird is plus 6.4, this bug's got to be minus 29, because they're going in opposite directions. And then finally, what's their combined final speed? Same thing, it's a collision problem. Initial momentum is equal to final momentum. So before the collision, we have mass 1, v1 initial, that's for the bird, plus mass 2, v2 initial, that's for the bug. And now afterwards, they have a combined mass, so again, completely inelastic collision, and a combined speed. So this part here is the initial momentum. This part here is the final momentum. So do a little bit of algebra and figure out what the combined final speed is. Okay, so really similar to the railroad car problem. The only difference here is the bug is actually moving towards the bird, whereas in the railroad car one, the coal was not moving horizontally, it was just dropped straight down. So a little more complicated, but it's the same idea. Okay, next one. A kid at a junior high cafeteria wants to propel an empty milk carton along a lunch table by hitting it with a 3.1 gram spitball. Okay, so the mass of the spitball, 3.1 grams, divide by 1,000, so move the decimal point over 3 spots to get it into kilograms, first of all. If he wants the speed of the 40-gram carton, okay, so spitball, carton, same thing, it's 40-gram carton, so move it over 3 spots to get into kilograms. Okay, good. Let's see. If he wants the speed of the carton just after the spitball hits to be 0.33, okay, so that's the combined speed. After the spitball hits the carton, we want it to be going 0.33 meters per second. At what speed should the 3.1 kilogram spitball hit the carton? Okay, so this is similar to what we did before. It's just we're given the final speed of the combined masses. We've got to work backwards to figure out the speed, the initial speed of the spitball, and we're assuming that the carton is starting from rest. Okay, let's draw this out. Okay, so here's what I have. Here's the mass of the spitball. We want to know how fast it was traveling initially to get this carton, which was initially at rest and has a mass of 0.4 kilograms, to travel with a combined speed of 0.33. Sometimes it helps to have a picture. So here's a carton with a spitball attached, moving with this speed. This is after the collision. Before the collision, here's a spitball traveling towards the carton. The carton's initially at rest. That's the initial momentum here. That's going to be equal to the final momentum over here. So it's another completely inelastic collision. So mass of the spitball, velocity of the spitball initial, and I could write mass of carton, velocity of carton initial if I wanted to, because that would be, the momentum of the carton. But it's not moving, so it doesn't actually have any momentum. So the initial momentum of the system is just contained in the spitball. And then afterwards, we have a combined mass, mass of the spitball, mass of the carton, and then they have a common final speed. So it's a collision problem. That's how I know to use the conservation momentum concept. And then the only thing that I don't know is the initial speed of the spitball. So you have to do a little bit of algebra to figure out this term, but you know everything else. Excellent. Okay, so next one here, we have a 22-gram ball of clay, so again, change that to kilograms, traveling east at 3.5 meters per second, collides with a 35-gram clay a ball of clay traveling north. Okay, so this is a two-dimensional collision. It's a little different than what we've done before. What is the movement direction of the resulting blob of clay, the direction that it travels? And then also, part B, what is the speed of the resulting blob of clay? Okay, so it's actually easier probably to get part B and then work backwards to get part A. All right, let's sketch this out. Okay, so here's the one that's going east. Here's the one that's going north. I call this mass 1 and this mass 2. And then after the collision, they're going to head off in some direction. Part A is what is that direction? Okay, so whatever momentum we had in the x direction beforehand has to be equal to the momentum afterwards in the x direction. Same thing for the y direction. Now before the collision, I'm going to do these separately. So before the collision, the only momentum that we had in the x direction was because of this one. So the initial momentum in the x direction is equal to the final momentum in the x direction. And again, the only momentum in the x direction initially was because of mass 1, because mass 2 is not traveling in the x direction. So I could say m1 v1 initial, that's the momentum before the collision just in the x direction. Afterwards, we have mass 1 plus mass 2 times their combined speed in the x direction. So really we're doing what we've done before with these completely inelastic collisions. We just have to do it twice. Now as far as the y direction goes, the initial momentum in the y has to be equal to the final momentum in the y. And the only momentum in the y that we have before the collision is because of mass 2. So I could say mass 2, velocity 2 initial, and that's just traveling in the y direction, would be equal to mass 1 plus mass 2 times their final speed in the y direction. Okay, excellent. So this will give you the final speed in the x direction. This will give you the final speed in the y direction. So that's perfectly good, but we want the overall speed. So we know the x part of it. This would be the x part of the speed. We know the y part of the speed after we've done the work. To get the overall speed, you have to use Pythagorean theorem. That's probably the easiest way. So velocity x squared plus this velocity y squared is equal to the overall speed squared. And then take the square root of the left-hand side to get the overall speed. And that'll give you the overall speed. Okay? Excellent. And then to get the angle, you can go back to this triangle and pick any way that you want to. I mean, now you know the x part, you know the y part, you know the overall part. You could use sine, cosine, tangent, whatever you want to get this angle. Okay, good. So similar to what we've done with inelastic collisions, it's just a little more complicated because we have two directions. Okay, so in the last one, we have a firecracker in a coconut blows the coconut into 3 pieces. So that's an internal force. There's no momentum before this explosion. There's no net momentum afterwards. So no net before, no net afterwards. So 2 pieces fly off south and west. Okay, good. And they have equal mass. And they fly off at 25 meters per second. We want to know something about a third piece. The third piece has twice the mass as the other 2. What is the speed of the third piece? And then what is the direction of the third piece? All right, let's take a look at that. Okay, so here's the picture. This is just M here. There's another M over here. We don't know the masses. We just know that they're equal to each other, so I called them M. And then a twice as massive one has to fly off this way. So again, there's no momentum afterwards, so there can be no momentum. There's no momentum before. There's a internal force because of the explosion, so there's no net momentum afterwards. Individually, this has momentum, this has momentum, this has momentum. You add them up, though, they add up to 0. Okay, so this one flies off south. This one flies off, I think it said west. I drew it west. It doesn't matter if it was east. It's the same problem. Okay, so these are at 90 degrees to each other. So as far as the angle goes, if you have some momentum this way, this one's going to have some momentum in the x direction. The y direction. This one has momentum in the y direction. This is going to have the same momentum in the y direction. This one has momentum in the x direction. This 2m is also going to have the same amount of momentum in the x direction. because this is 25 and this is 25, same mass, this one's going to have to go at 45 degrees. I can show you a more rigorous method in just a minute for that. So we can figure out how much momentum this one has going this way, and because we know it's equal to that one. So let's look at the x direction first. So we've got an m times 25 meters per second. That's the momentum after the collision this way. It's got to be equal to the same momentum of this one in the x direction afterwards. And this one is 2m. And then times whatever speed we have in the x direction for this one. Remember, this is the overall speed. It's got an x part and it's got a y part. It's really similar to the collision one that we just did. Okay, so this mass times its speed, that's the momentum of this one going that direction. This 2m times the x part would give you the other one. So this will show you that this speed is 12.5 meters per second. You can do the same thing in the y direction. And then you don't need to know the m's because they cancel out. In the y direction, same idea. You've got 25 going this way, so m times 25 down. That has to be equal to 2m times this vy. Okay, and then the m's cancel out again, and you see vy also turns out to be 12 meters per second. So if the x part is 12 and the y part is 12, you know this angle here has to be 45 degrees. Now the overall, 12.5, I think I said 12. So the overall speed afterwards, same way we did before, x part squared plus the y part squared, get the square root of that, to get the overall speed. Okay, that just gives you the x part and the y part. Okay, excellent. So it's a good chapter. It really comes down to two genres of problems: the impulse type, where there's some kind of outside force, and then when there's no outside force, we have collision problems. And it's sort of like balancing your checkbook. The initial momentum's equal to the final momentum. So, set it up with a nice picture, write down what you know, and go from there. Okay, thanks for listening. Talk to you soon.